And our outline is we'll talk about a little bit of a motivation. What is hydrology modeling, and what are the kind of few different ways you can come at it, and why might we want to bridge machine learning and physical modeling approaches. And then we'll describe how we go about that here at Upstream Tech. And finally, we'll show a case study diving into some examples of what that looks like in the real world. And we'll wrap up with some question and answers. Throughout this whole time, there is a Q&A button in your Zoom webinar. Feel free to ask questions throughout the webinar, and we'll follow up and answer those at the end. All right, let's dive in. So first, a little bit of background and motivation for why we want to try to bridge machine learning and statistical approaches to gain reliable streamflow forecasts. So for us here at Upstream Tech, we use models to make hydrologic forecasts, specifically river flow forecasts that are forecasting over the short term, roughly 10 days out, all the way out to seasonal, up to 6 months ahead, about how much water we'll have in our rivers and streams, and then also what will the water quality be in those rivers and streams in the days and months ahead. This is used by utilities to help plan their power production and their electric grids and systems. This is also used by environmental conservation groups to target their restoration efforts to make the most of their conservation dollars, and also by source water utilities who are interested in ensuring clean and safe drinking water. So that's why we want to have models. What is a model? A model is a simplified representation of some system. In our case, we use models to represent river basins and all the hydrology, all the water movement that's going on inside river basins. So in these models, we're putting in inputs, and in our case, these are things like the weather and the land conditions. And then we use those models to see how those weather and land are going to interact, and ultimately output some quantities that we care about. In our case, the total streamflow and streamflow forecasts, as well as what will the water quality be in terms of temperature, dissolved oxygen, and other metrics that we care a lot about. So that big model in the center there, that is the question today about how do we actually build that model? What goes into that box that we have there, and what sort of approach should we take to building that system? When it comes to models, there's a big variety of different types of models and ways to categorize them and ways to build models. Most of the time, this is something that's implemented as computer code in some software, although you can build a real life model as well. But one really useful way to categorize and think about models is this distinction between physical and statistical models. So a physical model is a model where scientists have written down relationships. Another word for these would be equations. And then we build up the model by connecting many different equations. For example, in a hydrology model, we would have equations for how water percolates into the ground. We may have other equations for how water evaporates and transpires out of plants, and some more equations that relate temperature and precipitation to snow accumulation and snow melting. And so then our model would be a sum of connecting up all of these different equations together. In contrast, in a statistical model, we do not impose those relationships beforehand. Rather, we collect a large data set of example data. In this case, it would be all of the observations of the weather and the land connected up and lined up with observations of streamflow, and then provide that data to a learning algorithm which can learn the relationships by studying that data set. So another name for these types of statistical models is machine learning, or sometimes it's called data-driven. Back over in the physical side of the models, as I was describing these equations, you may have recognize that each part of the system that we are modeling is very explicitly represented in the model. So you can point to a place and say, this is where we keep track of how much snow water equivalent we have accumulated in snow. And here's where we keep track of deep groundwater accumulation. In a statistical model, you don't necessarily have a particular place that you can point to in the model and say this is exactly where it's handling, say, snowmelt. In a physical model, it's also true that while data is not used to create the relationships, there are some knobs or numbers within those physical equations that need to be set correctly. And those knobs, for example, are things that say control how quickly plants will transpire water back into the atmosphere. And so we use data to calibrate those numbers in our physical models, sort of similarly and analogously to how we would use data to learn the relationships between the inputs and outputs in a statistical model. A statistical model is more flexible. It has, because we haven't imposed the structure of the equations and the relationships beforehand, it can learn a much broader set of types of relationships. Now, this can be a good thing or a bad thing. It can allow the model to learn a relationship that couldn't be possible out in the real world. And that's a possibility with a statistical model that is generally harder to do, to have that sort of deficiency in a physical model. In a physical model, in addition to the sort of explainability piece that you can get by looking at particular parts of the system, because it's built on physical equations, people often have more inherent trust that it's going to behave realistically in new conditions. Say, when we see a storm that's so big, bigger than any storm we've ever seen before. So why might we want to use a statistical model? Accuracy is a really strong argument for using a statistical model. What we're looking at here is some results of some research that we've published in open access journals. And we did the research about a year ago, and it got peer reviewed and finally published last fall. And the results of this research showed that a early prototype neural network, so machine learning statistical based model, was able to be more accurate than a model that has been a workhorse model for many, many years in hydrology that is more on the physical side of the spectrum between physical and statistical models. What's more, this evaluation was across hundreds of basins all across the US, and the neural network statistical model was at a really distinct disadvantage. It had never seen any data from any of the basins where we were evaluating it in. So it had only seen data from other basins in different locations. The traditional model, the SAXMA, Sacramento Soil Moisture Accounting Model, had been calibrated or given data directly from the basins that it was being evaluated in. And despite this, the prototype neural network model was able to be more accurate. So if we're using these models to make forecasts and predictions about the future, we really want a model that's going to be as accurate as possible. But on the other hand, we want these qualities that we often associate with physical models, like physical realism, so that if we move into new, unheard of conditions that we've never seen before, our models are still going to work reliably. And then in addition to that, we'd really like to be able to interpret and understand why the models are giving the answers that they're giving us. Not just get a number out, but be able to look and see why this model produce the forecast that it did. So that's really our motivation here today. Can we bridge these two types of models in order to get the best of both worlds and have models that are able to produce very accurate forecasts, be interpretable and reliable in new conditions? So I'm going to describe some ways that we here at Upstream Tech have been tackling this problem. First, a little bit about how we go about our modeling approach at a high level. So similar to that diagram you saw earlier, where we have inputs on the left, outputs on the right, and the model in the middle. Our inputs that we use are the standard meteorological weather inputs that go into almost every hydrology model. So this is your precipitation, your temperature, humidity, wind, pressure, all of that. In addition to that, we also input satellite data that can tell our model descriptions of things about the land surface. So how much vegetation is there? How much snow cover is there? What land cover types are there? What are the soils like? And this can tell our model information that it needs to know to understand how weather is going to interact with the land to ultimately produce streamflow. At the core of our model, we use a statistical-based approach that is a particular type of neural network that is designed to work very well on sequence data, so data that comes over time. And what's important about that is that allows the model to, when it's making a forecast for today or tomorrow, to have the history and take into account what's happened in the past. And we know that's very important. For example, if it's been raining a lot and it rains 1 inch, then the amount of stream flow is going to look a lot different than if the past 2 weeks have been totally dry and I get 1 inch of rain. So that's the overall pieces of our modeling approach. And now I want to kind of dive into some of the thinking behind how we start bridging them together. So we're at a time now where a few different forces have come together to make what I'm going to tell you about now possible. So the USGS, along with many other gauging operators all around the world, have been collecting streamflow data for decades and decades now in many, many different sites and doing quality control on that data. And so we now have decades of streamflow records across hundreds and hundreds of basins. And there's a plot here on the right that I'll show you some more of that's showing 1 point for every single stream gauge in the United States that we have a really long record and really useful record for. We also now have new and further developed tools in machine learning that allow us to analyze these data. And finally, we have computers and the cost of computing that has gone down enough that we can analyze lots and lots of data using machine learning. And what that enables altogether is for us to apply these machine learning techniques across these very large data sets to search for relationships that are true across space and time. So I'm not just looking for how does precipitation relate to stream flow in my one particular basin. I'm looking for how does precipitation interact with temperature and with vegetation on the ground and all of the other inputs to produce stream flow anywhere in the world. And those relationships that are true across space and time, that at its core is a physical relationship. And so that's kind of the key piece. Now that we have the tools and data across lots of places and lots of conditions, we can now start looking for relationships that hold in a broad set of conditions. And that starts to sound a lot like a physical rule, a physical law. So I want to show some examples of the data and the diversity of data that we have that we can start to look at. So each of these next slides is going to be some condition about the basin that, and each point is colored based on the variable that we're looking at. So here we're looking at the average elevation of each basin. We can see we've got a really broad range of elevations of basins in our data set. Similarly, in terms of the seasonality of precipitation, so how consistently do we get rain, or do we get all of our rain or snow in particular months of the year? There's a really broad range of that as we go across the US. When it comes to snow, there's a big diversity of conditions about whether that snow falls as precipitation, as rain or snow. in terms of the total amount of precipitation that falls, we've got some really, really dry regions and some really wet regions. And the time of year when precipitation happens, when is the driest times and when are the wet times in the year, that's really different as we move across the United States as well. So coming back to this, when we search for these relationships now, if we can find a relationship that's true across that really vast diversity of basins, and that relationship holds across time and as we go between these different basins, that means we now have a relationship that between our inputs, our weather data and our land surface information and our streamflow, that is something that's coming to look a lot like a physical law. Now, how do we know as we move between these different basins, how do we know whether we're in a basin that has a high elevation, lots of vegetation, not very much vegetation, lots of snow? Well, satellite data can give us those answers because satellites are constantly orbiting the Earth and collecting information that is highly, highly relevant to hydrology. So what we're looking at here is a satellite data metric that tells us about vegetation, and when it can also tell us a lot about snow. And so the colors that are white colored here in these images, this is where there is snow. Where it's brown or yellow or light tan, this is where there's bare earth. And then where it's green, there is vegetation, and the really dark green is extra dense, healthy vegetation. And so in these three images over the course of a spring, we can see how the satellites can see the snow cover in this high mountain basin, and then the snow quickly melting over the course of the spring and the vegetation growing up in its place. And so these data like this that comes from satellites can help us characterize as we move across all of these basins to help the model know what type of basin we're in and how it should react when the weather inputs are fed into the model. So tying this all together, our approach here to bridge machine learning and physical modeling approaches for hydrology is something that's been described as theory-guided data science. And what this means is we apply our physical knowledge of hydrology that's been built up over decades and decades of scientists who've come before us, who've been studying hydrology and river basins, and we apply that to statistical approaches so that we can use the strength of those statistical approaches, but make sure that we're applying them correctly and gain the best of both worlds. So what does this actually look like? One of the biggest ways we do this is we constrain our statistical models using hydrologic theory. So that means we don't put any inputs into the model that shouldn't be hydrologically relevant. So I'm not gonna go put in, say, the median income of people who live in this basin, because the hydrologic science tells me that should not at all be relevant to the amount of streamflow I'm seeing. It also informs how we construct the actual statistical model and the way that we do the training process as well. A key piece of this is ensuring that the model's inputs will change when the world changes. And so that's why we use data such as the satellite data that shows us, for example, if as we are now starting to see in some particular basin that the snow is melting earlier in the year, the satellite data will be able to see that, and our model, if it has that satellite data as input, will be able to react. So this can allow us, under a changing climate, when we use our model that is trained across hundreds and hundreds of basins, to be able to react as one basin changes to be more like, and have the climate more like some other basin that has perhaps, say, drier or gets more rain than the basin used to. Finally, we can take our models and we can look inside them to make sure that those relationships that they've learned are physically realistic. And so that's what I'm going to do here in our case study, is actually inspect the relationships that these statistical models, these hydrologically informed statistical models, have learned on their own, and make sure that those relationships line up with what we know should be the case from the hydrologic sciences. So let's dive into that in a case study. Our case study location is Spanish Creek. It's up in the Sierra Mountains of California. This is a snow melt driven basin. So we see large snow accumulation over the winter. You can see that in the animation of that same satellite vegetation index that we saw earlier. You can see that here as we move into January. You can see the snow falling. Now in February, there's snow all over the basin. And then as we move into March and April, we can see that snow starting to melt back down. And that melting snow is what turns into runoff. And we'll see the model learning that and learning those relationships momentarily. On the left here, we have an example of a prediction that came out of our model aligned up with the actual true observations. And this is just an example of some of the output that comes out of our hydrology models. It's predicting both the most likely value that it thinks will happen on each day, as well as a range of probability distributions about the possible values, because our models know how to describe how confident or uncertain they are given the particular conditions that we're seeing that day. All right, so here is the plot that we're going to spend a few slides digging into. So don't worry if there's a lot of squiggly lines at first. So the goal of this plot here is to really ask that question: how are our inputs influencing the output? Which inputs about streamflow, about weather, about land surface information are influencing the streamflow that we see come out in the river? More particularly, we take a period of time, and so it's this time where the black bar is from April through May of 2019. And so what this plot is asking the question: which inputs from which times, both during that time period and leading up to that time period, contributed to more streamflow in the river during April and May, and which inputs contributed to less streamflow? So the lines that we have plotted here are not the actual values of the inputs that go into the model. Instead, they are the relationship, the influence that input on this particular day had on the output and the total amount of streamflow during April and May. So what we're seeing up here is these large spikes in the pink line, which is precipitation. And this is happening back in the winter. And so what that means is these spikes are positive, they're above the 0 line. And so that means they're having the precipitation inputs on these days back in January, February, and March had a large positive impact on increasing the amount of streamflow in April and May. So what does that mean? That is snow happening in the winter. So when we take our hydrologic science knowledge hats and put them on and look at this plot, we would expect that snow precipitation that fell back during in the winter when the air temperatures were very cold would fall as snow and would stick around so that later it can turn into and be melted and turn into streamflow. We can then go look about what's happening in the springtime concurrently at the exact same time as the output that we're looking at. And what the dominant lines we see here are this brown line here that's having a positive influence, and that is this SRAD, or solar radiation, which is the total amount of sun beating down on the earth. And so what we're seeing there is the sun melting this snow. And so what we can see in this, when we look at these two patterns together, is that the model has learned to pay attention to precipitation falling during the winter when it's cold and store that precipitation up as snow so that later it will have a positive, very large positive influence on causing more discharge to come out during April and May. Now, there's a few other lines here, which I won't fully interpret, but we can go through all of the different inputs that we have here with this type of plot. And we can apply these tools to new locations and to any sort of predictions that we're making with our hydrologic models. And these tools are just one way that we can start to look at what the model has learned, what are the relationships that it's learned to pay attention to, in which conditions, and we can double check that those relationships line up with what we would expect as a physical scientist who knows about hydrology. So this plot is looking at the relationships that the model has learned between the inputs and the outputs. But we can go one step deeper and actually open up the model itself and look at what it has learned to keep track of. And so this is some research that came from some collaborators that we work with in academia, and they looked at the internal states of this neural network model. And the model actually has a number of states inside of it. We call them memory cells, and they're able to keep track of values that the model learns is relevant to making predictions. And so in this case, it turns out that there's a memory cell, and this one happened to be memory cell number 4, that the model learned that it should keep track of something that stays very low during the summer months. And then as the temperatures start to get colder and colder, which is what we're plotting here down in the bottom plot, and we start to have precipitation, which is not plotted here, but was happening, then this memory state goes up. And then when this memory state tracks very high for a while, and then ultimately, as we get into warmer times, it moves back down again. So at no point did the modelers or we tell the neural network that it should keep track of something called snow. And it doesn't actually even know that what it's tracking looks very much like snow. But that's what it's learned. It has learned that there's some quantity that it should keep track of that is very relevant to making predictions. And that quantity goes up when there's precipitation that happens when it's cold, and it melts and it contributes to streamflow when there is warm temperatures. So there's another example of actually opening up the neural network and really looking inside of our statistical models to make sure, with our theory hydrologic science hats, to make sure that what it's learning to pay attention to and the relationships that it has learned are really realistic. So can we really have the best of both approaches? By no means have we figured out all of the possibilities and the ways that we can do this in the hydrologic sciences, but I believe that theory-guided data science provides us a path to joining physical science from the hydrology world and physical modeling with the best that statistical and machine learning has to offer in order to give us reliable streamflow forecasts. To kind of sum up this approach, we use the physics to define the parts of the model that we know and we're confident in, and then we allow computers to learn the relationships and learn the parts that we don't. And finally, neural networks and these statistical models are often described as a quote-unquote black box model. And I posit to you that it's actually only a black box until you open it, and that as these approaches have received relatively less research, we just haven't yet built all the tools to open these black boxes. And in that case study, I hope you saw some first examples of these tools that we can use to open up the black box of neural networks, show that it's not really a black box anymore, and join together the best of physical modeling and statistical modeling for reliable streamflow forecasts. Thank you all I'd like to open it up now for questions. So you can find the Q&A button down at the bottom of your webinar controls. And I'll enjoy a nice sip of water here, and we'll take questions as they come in. All right, so we've got a great question here about could a modeling approach like this be applied to a more managed hydrologic system, for example, streams with dams or water withdrawals? That is a fantastic question. We have done work about this, particularly looking at human withdrawals for agriculture and rural development. And the models, it's really, actually very fascinating. We can take the models that are trained across those hundreds of basins that are unmodified, and we can go apply them into a basin where there's human withdrawals from the system, and we can see them actually predicting differently than what we would see in what we see in the Streamflow gauge data. For example, having higher summer base flows. And then we can do some more training with that data from these modified basins where there are withdrawals. And then the model learns to track those patterns of human modifications of the system. Now, so this works really well where the stream flow is not regulated by a dam itself. For below dam approaches, a model just like this isn't what you need, but we are actually in the process of creating models which learn to operate just like a human dam operator, but that is more of a research and development process. So we have a kind of follow-on question to that. How does the model account for anthropogenic factors influencing stream flow, for example, groundwater withdrawals? So what we have seen so far is the model is learning to react to the inputs that it does have available in order to understand what the human influences probably will be. And so, for example, the model is able to see things like air temperature. And so it can learn that when I'm seeing sustained days of long amounts of air temperature, high air temperatures in a basin where we have trained it to giving it agricultural data or data from an agricultural basin where there would be withdrawals that were driven by air temperature, then it can learn to respond to those and understand that it should be taking more water out of the system to compensate for what an irrigator is probably removing, or multiple irrigators are probably removing from the system. So we have another question, wondering if we are using neural networks to predict any other measurements related to streams. Great question. So we've done some really exciting work with a group called Xylem, and together we did some research and development testing whether we can use these same approaches to predict water quality metrics. The results of that were really exciting. So in natural flowing streams, we were able to predict the water temperature and the dissolved oxygen content of the water really excitingly accurately as well. And those predictions were actually coming from the same model structure and using all the same inputs. And that makes sense from a water quality science standpoint. The quality of water in stream somewhere is related to the conditions in the upstream basin, just in the same way as the quantity of the water in the stream is related to the conditions of the upstream basin. But it was really exciting for us to be able to see that the same models and the same structures and the same setups could forecast additional water quality variables really well. We're working on further research and development to add in other water quality variables like nutrients and algae into that mix. Question about the computational requirements. What are the computational requirements to run these models for, say, a very long time period? For example, 50 years. So the computational requirements that take the most work is really the training process of the model. So giving it data from many basins in order to do that training process that I described. And then once you have a model that has learned those relationships, we can go apply it to new places really rapidly. So it takes us a couple minutes to pre-process the input data for a new basin. And then to actually run the prediction, once we have the inputs, it takes a matter of seconds, even for, say, 50 years at a daily time step. If you were to go up to, say, hourly time step across 50 years, it would be, maybe 15 seconds or so. But the efficiency of the model itself is really usually not the bottleneck. It's much more the pre-processing of all of the input data sources that we need to collect in order to get them to the model. We've done a lot of work at Upstream Tech in building distributed software systems that can run across a cluster of many computers to collect all of that data that needs to go into the model. All right. Just reading through, these are great questions. Thank you all. So a great question. Are there any cases that come to mind where the approach doesn't work well? Why? So the biggest problem we see is when there are modifications to the Streamflow that aren't present, that we're not telling the model about, essentially. So dam regulation is a key example of this. If our models do not have inputs that describe what dam regulation will be happening, then the model will, as you would expect, not do well at all. Another requirement is that we have good data. So high quality data is really important for statistical models. Fortunately, in terms of weather data and stream gauge measurements, there is large existing public data sets that are really high quality for, particularly in North America, for this type of data. As we move out to the rest of the world, that becomes a little bit more sparse, but these existing data sets are really good. What can be a challenge is if somebody would like us to make a model for some particular location, but the data that they have for that location is inherently very noisy or has a lot of errors in it in themselves, then we have to spend some time cleaning up that data before we give it to the model, because data we give to the model, it will, if we're using it as the ground truth gauge observations, then it will just do its best to predict that data, and it doesn't know that that is wrong. So we have to apply our hydrologic science and common sense to the data that we give to the model when we're training it. Could it happen that the statistic model part of the model adapts to changes through climate change and predicts something that we cannot yet explain physically because the model already, quote unquote, knows more about climate change than you can physically explain? This is a really interesting question. So one potential for these models is So going back to why we build models to help better understand the world, and that can make us, we can use that in terms of better forecasts. And we can also, if we have a good model, look at how that model behaves. And sometimes that can help us learn something about the real world, the system that we're modeling. We're really only starting to scratch the surface on this, but this is something that could be really, really exciting. So hydrology doesn't have, unlike a number of other sciences, hydrology doesn't have a set of like unifying laws akin to, Newton's laws of physics, the way that many other sciences do. And it's possible that those just don't exist out there, but it's also possible that we haven't found them, and that by using and observing a machine learning model that has learned new relationships, we may be able to learn something new about how hydrology actually works. We recently hired a new director of research on our team who has spent a lot of time looking at this world, and this is something that we're really actively investigating. So far, we have not discovered anything by observing our neural networks about climate change specifically yet, but it's a possibility. Reading through these. Thanks for all the good questions, everybody. So in the work Upstream has done, is there evidence of a warming trend or drying trend in the southwest of North America? So we really have been focusing our forecasting and modeling efforts on the 10-day to 6-month ahead horizon. And so we haven't really looked at that sort of super long decade scale trends yet. But from the data that I've seen in terms of climate analysis, essentially the NOAA consensus from our atmospheric centers seems to be the western half of the country getting hotter and drier, and the eastern half of the country getting wetter and is receiving more precipitation. All right. Well, we have gone and hit our 45-minute time limit. I want to thank all of you for joining us today. If you have additional questions, please feel free to reach out to Alana or myself. You can also check out the website that we have for our hydro forecast product, hydroforecast.com, which is where the tool that we use that uses all of these models. And we know we weren't able to get to all the questions here, so we'll reach out to you if we weren't able to answer your question on air. And if you have questions or would like to see about what hydro forecast or these models could do in your basin, please do not hesitate to reach out to us or email us. My email is alden@upstream.tech, and Alana is alana@upstream.tech. So once again, thank you all for joining us, and we hope to have a great rest of your day.